14.7 again, and 14.8. 14.7 will help us find the local maxes, local mins, and the saddle points of the multivariable function. And we know step one, find the critical points. We'll set fx and fy equals 0 and solve the system. And I should put that here too. We will solve the system of equations that stems from this fx equals 0 and fy equals 0. Once we solve that system, we can find those critical points. Then we'll use the determinant d to determine whether or not it's a saddle point, min, max. Saddle point if it determines less than 0. It's a local min if it determines greater than 0. And fxx is greater than 0. It's a local max if it determines greater than 0. And fxx is less than 0. And again, I just want to reiterate that I drew these little concave up and concave down portions, so it helps us remember whether we've got a local min and a local max, because this means second derivative is positive. That helps us remember that. So here's the function we're going to work with. It's a function of x and y, and I've got 2x to the fourth plus 2x to the fourth y plus y squared plus 3. And the question is, find all the local maximum points, local minimum points, and the saddle points, if they exist. If they exist. So we could come out in the end and just only have saddle points. Or maybe one local min and that's it. Or a local min and a local max. So the critical points, we never know how we're going to get until we start working out the math. So our first step, step one, let's find the critical points. So step one, let's set fx equal to 0. What's fx? 8x cubed plus, be careful there, 8x cubed y. Was everyone okay with that? Very good. Is that it? Ah, cool. I'm going to put the word and. I just write the word and because it is a system. So we're thinking it's got to be points that make that true and make this true. What's fy? So it's the fourth plus 2y. That's it, right? Equals. Now we got to solve this system. Maybe the only challenge with this section is solving the system of equations. So we got to solve this system here. That's where we go to one portion, left or the right, doesn't matter where you start. Factor if you can, solve for a variable, and then substitute into the other. Sometimes one looks easier to work with than the other. Don't they look basically the same? I'm going to start on the left, okay? And when I start playing with this one, I think it helps if we factor. What can I factor out of that?
8x cubed.
Awesome. 8. Factor out an 8 and an x cubed. I'm left with 1 plus 1. And I'll set it equals 0. So here's our starting point. So I notice two things are happening. One of them is, if 8x cubed equals 0, then what does x equal to? All right, we got it if x equals 0 for that part. What's the other scenario? If y equals -1. We'll deal with that separately, so we'll come back to that. I didn't want you to think your pair is 0, -1. This would be wrong if I went like this. My critical point is 0, and then the y is -1. No, that's the error I don't want you to make. These are so I got to take this and put this over here, see what corresponds with it. And then I'll come back to this. What was this value? Y equals -1? Making that true? Good. I'll write that down when we come back to it. So we'll come back to this. We'll come back to you. What we're doing right now is exploring this x equals 0. So let's take this, where are we going with it? All the way over here. And if x equals 0, what do you get out of this? 2 times 0 to the fourth plus 2y equals 0. What's y?
0.
Aha! There's our first critical point. If x equals 0, then y equals what? 0. That point makes both of these equations equal 0. That's our first one. Got one. This has at least one critical point. Okay. Now we got to explore the what? Now we have to explore this one. Okay, so we're done with that, right? check, you're done. We saw what came out of it. If x equals 0, then y equals 0. And this is what's going on here. We have to put it all the way over there to figure it out. Now come back. What about this? What if y equals negative? Does that make sense? Take this, where you going with it? Get this out of the way. So it doesn't confuse us, because you were done. Y equals negative 1. Right there. I erased that 2x to the fourth by accident, sorry. What do we get? 2x to the fourth plus 2 times negative 1. Can you help me solve this? 2x to the fourth equals
2.
divided 2 on both sides.
X equals to plus minus 1.
Man, you are good. So that's my worst fear, that we miss a critical point. Sometimes people just do that. That would have been true if that was x cubed equals 1. But it's got an even root, right? Square root both sides, that idea of fourth root of both sides. X is equal to plus or minus 1. This is what happened with x squared equals 1, x to the fourth equals 1, x to the sixth equals 1. But if it was x cubed equals 1, we only got one value. We just found 2 more critical points. So there's 2 more, what are they? Both of them have y equal to negative 1. But the x values are, one of them's a 1 and the other one's a what? There you go. These are the 3. Step 1 is complete. Step 1 is complete. So we're done, we got all the math done. Now we got to deal with the determinant. Oh, is this point, this point, this point. Are they saddle points? Local maxes, local mins? We'll find out. Can I erase all the algebra up there though? I will. I'm going to leave the fx and the fy. I'll leave that up there. Get this thing out of the way. Alright, you're out. You're out. Good. So let's go find the determinant. D is fx, fyy, fx, fyx, but really just this times this minus this times this becomes fxx, fyy. I've seen this before in test 2 before. What am I missing? It's that partial derivative, the second part. These are all second partial derivatives. So what is fxx? I can do it right here. I want to leave some room so we can write down what these are. What's fxx? 24x squared plus 24x squared y. Does that echo that? Yeah, that can be a little weird. Like, how do I deal with that? That y stays constant. What's fyy? I'm looking around like, where's that y? It's just 2. That was easy. And what's fxy? Or fyx, either one. What's fx with respect to y? 8x cubed. You could have done fyx. 8x cubed. Let me write this out. You got a 24x squared plus 24xy, you need a factor there, times 2, subtract 8x cubed, and then you got to raise it to the second power. You can leave it like that, because all we're doing is plugging in numbers. Alright, what happens when I plug in a 0 and a 0?
Isn't it 24x squared?
Oh, thank you, 24x squared y. If I plug in 0 and 0, what do you get out of this?
0.
Does it come out to be 0? 24 times 0 plus, that becomes what? 24 times 0 times 2 minus that. So we get 0 minus 0. I guess with that, because we're getting the determinant 0, it's what?
Inconclusive.
Inconclusive. What's going on there, so we're just going to put that. Inconclusive. If it came out negative, we would have just said it's a saddle point, or positives, we would have dealt to see if it's local, min, or max. How about 1, negative 1? What's going on at 1? Negative 1. And 1, negative 1, I get 24 minus 24. That's turning to 0. What ends over here? Minus 8, you plug in a 1, and you square it. That's minus what? Saddle point? I mean, because this is turning into a what?
0.
Isn't that 0?
Mm-hmm.
24 plus, this is at 1, negative 1. 24 plus negative 24 times 2, 0 minus 64, negative 64, your saddle point. And we'll leave 0, 0 as inconclusive. You wonder, what do you do with that? The only other thing we can do is go explore it. You can explore with technology. You can graph it using WinPlot or Maple or MATLAB. You can graph it and look. What you do is you look at points right near 0, 0. Like maybe plug in 0.1, comma 0.1, or negative 0.1, negative 0.1. Plug it in here and then see how it changes, because what happens when you plug a 0, 0 in there? You get the number what? 3. You can exploit that way too, just numerically by plugging and chugging. Maybe that is something. That's how we can approach that. What's going on at negative 1, negative 1? What happens here? If we plug in negative 1, negative 1, does this stay 0? That stays 0. You put in a negative 1 here, you get negative 8 squared, but that stays what? So this is also what? There we go, we end up with 2 saddle points. But this was inconclusive. You notice when we plugged that in there, nothing came out of that. Right? Excellent. Hey, great job with that. Any questions on that? Alright, so now let's look at an application problem. I'm going to pull one from the textbook, and we'll approach it the same way and figure out what we can maximize or minimize. So what we're really doing right now, everyone, the remainder of today, do a problem 14.7, we'll do a problem, 2 problems at 14.8 with what's called Lagrange multipliers. We're going to stay here for now as we're optimizing. They call this optimization. We're going to give us some scenario, we're going to try to optimize it. Maybe you get the maximum value or the minimum value. These give locals, but if we only get one answer as our critical point, that could be the max or the min to a problem. So this is in section 14.7, and this is number 51. All right, so let me write this out on the board. This is what they write. A cardboard box without a lid is to have a volume of 32,000 cubic centimeters. All right, so a cardboard box, and when they said no lid, so without a lid, has a volume of 32,000 cubic centimeters. That's given to us. Or is to have it, they say. They say find the dimensions that minimize the amount of cardboard used. Okay, find the dimensions. That minimize the amount of cardboard you use. We'll get right to it. You can definitely do it with this technique right here. Our real work though is going to be right here, you'll notice. Right in here, you'll notice. Just make sure you know the deal to solve a system of equations. We'll get fx, we'll get fy, and all that stuff. This problem probably sounds familiar to something from Calculus 1. So you might be like, can I use Calc 1 techniques? The reason you couldn't solve this one in Calc 1, there was a problem like this in a book like this in Calc 1. But what they did was they made sure to tell you like, oh, it's going to have a square base. They wrote that. They're not saying that here, are they? They're just saying all you have is a cardboard box and has volume of this. So the key is that when we're approaching this problem, we got to figure out what function we're trying to maximize or minimize. In this case, we're trying to minimize, right? What are we trying to minimize? That's the function we got to set up. So what are we trying to minimize here?
Surface area.
Surface area. So when I call it A, we can call it like A of X and Y, right? Surface area. And we're just going to say, this is what we're trying to maximize. You can call it F of X and Y, but I'll call it area of X and Y. We should draw a picture to help us know how to deal with something. All right, here's a box. I'm going to make a box. I need some variables to throw down. You okay if I use X, Y, and Z? Okay, your X. Different from Calc 1, they didn't say square base, so I'm going to have to call that another variable Y, and then the height Z. Cool. So what's the surface area? Well, let's start with the base. What's the area of that base?
XY.
By the way, I'm going to put a reminder, there's no lid. So area is XY, there's the base, plus, how many I should shade this in? What's the area of that side right there? Y times,
Z.
and there's two of them. So plus 2YZs. Does everyone see that? Surface area. And there's two other sides. What's the other sides? I could shade those in a different color, maybe yellow. What's the area of this side right here? And then we'll have the opposite one as well. X times what?
Z.
Z. Okay. So two of those. And there's the area function. We're going to work this just like we did the last problem, piece of cake. Except I got a typo on the board. You probably spotted. This is the secret in section 14.7. Function of two variables. Area as a function of X and what? Y. As you can see, I have trouble. So before I start this problem, if I'm working a problem in 14.7, I got to make sure this only has two variables. So I need to put something in place of those Z's. But there should be enough information where we can do that. So let's go off to the side here and just put some side notes. Do we know anything else about this problem?
Yeah,
They give us some information.
X times Y times Z equals to 32,000.
There you go. That number 32,000, you notice we haven't used it yet. So they gave us some information about that. They call it, you want to know what they call it? They call it the constraint. Like under this constraint, it's like, okay, they're saying that the volume can be constrained to being 32,000 cubic centimeters. So over here is my notes. I'm like, well then I know, and I heard you say it, all right, thank you, that X volume is length times width times height. So X times Y times Z must equal
32,000.
aha. There we go. Can't we substitute something into this? So we get this thing all in terms of X and Y, and then we can roll. Because right now it's not working because this can only be a function of X and Y, and I got these daggone Z's there. So what's Z equals?
32,000 over XY.
Nice. Now it may look like, oh gosh, this thing's going to turn into a monster. Yeah, we'll hang with it, it won't be bad. It may look like it now. Well, we'll just, yeah, take it slow. We all know, go ahead, substitute, here it goes. Swing around here, you're going right there. And I'm also going to put you right there. And I have yet to do this, see? I haven't even gotten to this yet. We just got to get it all in terms of two variables. All right. So now I have area equals xy plus 2y times, up parentheses, 32,000 over xy plus a 2x times a 32,000 over xy. Is anything simplified? Nice. So you're getting rid of these. Now I do have a function of x and y. Area of x and y is equal to xy plus pi to the y's plus 2 times 32,000.
64.
So 64,000 over x plus pi by the x's. 64,000 over. There we go. Now we're ready. We're ready to start step 1. Get f x. Okay, A sub x. The first with respect to x, get the first with respect to y, find the critical points. And then we'll talk about whether or not we got to do this. trying to optimize the scenario here. All right. What's the first derivative with respect to x? So I'm going to call this a partial derivative with respect to x. A sub x there. A. Take the derivative, partial derivative with respect to x. That would just be a y. How do you do that?
Negative.
And you're good. Just think of this as x to the negative 1. Multiply the negative 1 in front. Decrease this by 1. Would be get x to the negative 2, right? Did everyone see that?
Mm-hmm.
But x to the negative 2, that means where is it? So I'm going to write it down at the bottom. So I'm going to write that. A lot of you see that. You're like, yeah, we get that. I got y minus 64,000 over x squared. This should be similar. That's y to negative 1. Negative 1 times 6,400 is negative 6,400. Y to the negative 2, which means it's negative 6,400 over. Right? Oh, and this was only with x. Thank you. So I'm going to stop there. Where do I set this equal to?
0.
You're the best. So when I get over here, remember I got to put and? That comes up over here. So what's the partial of all this stuff with respect to y? That becomes
X
x. And then
minus
the second part I was just writing, there we go. 64,000 over the,
y square.
and I set that equal to 0. And now it's just an algebraic manipulation game. Can we solve the system? We try to take solve for one variable on one side, substitute it into the other side. Doesn't matter what letter you solve for, really. I can solve for y here. What's y equal to? Y equals 64,000 over x squared. Where can I put that? I'm trying to solve this system. Take that and put it where? Right there. Okay, now we got a complex fraction, so I'm going to write this slowly. Take x minus 64,000 all over parentheses squared 64,000 over x squared equals 0. Oh, okay. Okay, maybe I'll set these equal to each other. X now equals 64,000 over a 64,000 times another 64,000, right? Over x to the 4th. Yeah, so how do you divide fractions like this? Call them complex fractions. Because you multiply the reciprocal, this comes what? Upside down like that? So I'll just draw an arrow here. You now have x equals this times this reciprocal, 64,000 times, flip it over, x to the 4th over 64,000 times 64,000. And one of these 64,000s do what?
Cancels out.
Cancel out. Just take a year out. So now x equals x to the 4th over 64,000. And we can finish that up right here. X equals 64,000 all over, whoops, x to the 4th over that. You want to multiply 64,000 times the x?
Mm-hmm.
I like that too. Hey, sometimes I always emphasize factoring, but I'm not so worried about factoring here, everyone, because yeah, get x equals 0. Isn't x equal to 0 solution here? But I wouldn't real life problem. Can x equal 0? So I'm not worried about factoring here. I'm just trying to get the actual number of x, the values where it's not 0. So I can divide an x on both sides. I won't lose like an important point. Cool. So that's why I'm not factoring here. But if you divide an x on both sides, that's okay, because x can't be a possible answer. 64,000 equals x cubed. And how do you solve that? Yeah, cube root. What's the cube root of 64,000? 40? Problem solved. So now to get y and z, just do what? Put them in? Where do we put them though? It's a mess on the board. All right, there's y. There's y. All right, x is 40. I'll go up here, you're 40. There's x. Y is, what's 64,000 over 40 squared?
1600, right? That's 1600.
I'm going to put it back in here.
40.
64,000 over 40 squared. Is that 40?
40. Yep.
Now we know why in Calc 1 they told all the students in Calc 1 it was a square base. Do y'all see this? Isn't that interesting? This would happen every time, by the way. Alright, and what's this? With an open top, with an open top. This is what you get. It turns into a square base. We just saw it. This is kind of neat. Where's Z? There, yeah, there it is. Right there. 32,000 x squared. 32,000 over 40 times 40. Well, that's not 40. Is that 20? Yep. Hey, what's interesting, everyone, these problems, you do every problem out of this section, I'm telling you, a lot of times you see symmetry in your answers. You see what I mean by symmetry? These came out to be what? Exactly the same. It's just really interesting. You go, what happens when you do have a top? It turns into a perfect cube. Symmetry. You know? Like 40, 40, 40. Or 20, 20, 20 in terms of the dimensions. It's really neat, but it's justified through this technique. Hey, great job with this. And what we're going to do for the rest of the class is talk about section 4.8, which is an awesome method called Lagrange multipliers, the Lagrange multiplier technique, that allows us to find these extremes. You might find it as a method, you go, well, we got this. And when it might be 10 times as fast or 10 times as easy to work that method. Plus, it focuses on finding the absolute, those extreme values. All right? So it's called Lagrange multipliers. Can I erase all this? Hey, cool. Hey, while I'm erasing, I'll fire this thing up. Just, there's only one image I wanted you to see before we put the theorem down, or the whole method. Fire up. So I'm going to erase all this. You're gone. Lagrange multipliers. What is this for? You can call it the Lagrange multiplier method. You'll notice the author just writes Lagrange multipliers. You'll see by the technique. This is a technique that allows us to find the extreme values. It can be minimums or maximums, but the absolute extremes. What's the whole idea behind this? So I wanted to hit this. Can everyone see this thing? Remember I talked about the word constraint in the last problem? The constraint in the last problem was the volume x, y, z equal 32,000. Remember that? So we're like, what if you're trying to maximize some function of x and y? But there's some, but given or under the constraint of, let's call it g. So the Grange multipliers technique says, all right, well, we're trying to see, of course, where's the highest value of f that's obtained where g intersects it. And then when you notice it's the highest number's right there. And what's that function's value, what, 10? And something else do you notice? Do you notice right here, they both share not only a common tangent. What are these two colors? Because I'm color vision. Is that red?
Blue.
Oh, this one's blue? What are these curves? They're red. Oh, thank you. I'm standing right here. I can't see these colors. So these are red and this is blue? Oh gosh, they all look gray to me or black. So anyways, but the red and the blue, they share a common tangent, but they also share a common normal vector. Isn't that cool? And do you remember the gradient vector? So they share this common gradient vector. So the whole idea is to be vectors being parallel, you can use a what? Just multiply one by a constant multiple? And that's the idea. You take f and g, set up their gradient vectors, you set them equal to each other, but you take one of the vectors and you put just another variable in front to represent the constant multiple. Cool? But that's the idea behind this. So I'll turn this off, I'll write it on the board. It's the idea of using gradient vectors. And we'll call, everyone, throughout this whole section, you want to call the constraint always letter G. Does that work? Now I'll turn this thing off. Let's call it constraint G. So what we're saying is the Lagrange multipliers method is to maximize some function of x and y, let's say. It could be a function of x, y, and z. Isn't that neat? Under some constraint let's call it g of x, y, and z equals k. And when I'm just writing k like it's some constant, you know? Like think of, just to give you an example of this, in the last problem, x, y, z equaled what, 32,000?
Mm-hmm.
So you could have used this method to solve that problem. Or you could try it later. But this is the idea. He goes, when you take del f, and we're going to set all the corresponding components equal to del g. That'll be the gradient vector of this function g right here. But we need to multiply some variable because it'll be a constant of one of these. I'll stay consistent with the textbook. With most textbooks, they use the Greek letter lambda. So would you put a lambda right in front of that del g? Just to say that's going to be that's another constant. By golly, if you hate that variable lambda, the Greek letter lambda, you could just use a letter like m. Make up another variable, c. That's the idea. It's going to be some constant. So we're going to maximize this, and when we work the problem, everyone, you're going to make sure we're just going to set, when we get del f of this component, we'll set it equal to this. We'll set this equal to this one with the lambda distributed to it. We'll set these equal to each other, and we'll list this constraint G. And all we got to do is solve that system. And it's pretty neat because this makes a lot of problems way easier to solve. Okay? So, and let's start with one. This is from the textbook. And when you find the point, on the plane, x plus y plus z equals 1. That is the shortest distance. From, they give another point. 2, 0, negative 3. And we're going to do two problems. We'll start with this one. Hey, could have I used section 14.7 to solve this problem? Absolutely. I want to point that out. The last section. We just got to know distance formula to get this thing started. Do you all agree? Find a point on a plane that is the shortest, there it is, distance from this point. Don't we need the distance equation?
Mm-hmm.
That's the function that we're trying to actually minimize. What's distance formula in three-dimensional space? So we can call it d for distance, right? Here's my f of x, y, and z. What's distance equal to? Square root of what? x1 minus x sub 2 squared plus y1 minus y sub 2 squared plus z1 minus z2 squared. There we go. That's what we're trying to minimize. Shortest distance. What's the constraint though? Look through the problem. There's got to be some constraint under this.
That point.
Yeah. This is this whole idea of this plane right here. I mean, a point's going to come into play here. We'll put the point in there. There's your constraint. Because it's a point on this what? That point just can't be anywhere. The point we're talking about has to be on this plane. So that's your constraint over here. We're trying to what? This is what we're trying to minimize. That's the function you're trying to minimize. This g over here is just the constraint. It's got to be constrained to that plane x plus y plus z. So you can write g equals x plus y plus z. You know, you got to put the equals 1. You can put that, you know, in terms of that. But this is really what you're going to take the the gradient of this. So I'll just put. I'll write this. I'll say this is our constraint. You can set it equal to g if you want. But this right here is g of x, y, and z. That's your g. Now, where are we plugging this point? In there? So I'm going to write it again. X minus what? 2 squared plus y minus 0 squared plus z minus.
Plus.
Yeah, that's. And when we got a 2, 0, negative 3 here. Alright, it says make that z plus 3. So far, so good? There's your f, there's your constraint. We're going to get some gradient vectors in a second. I do want to point something out. Do you recall this from Calc 1? That when it comes to minimize or maximizing distance, you can just minimize or maximize distance squared. You get the same answer. If you want to avoid that radical. Did you know that? You can definitely do it. So I recommend, if you want to deal with it radically, you can. It's just going to make your derivatives a little bit harder because of the radical. But you can totally maximize or minimize big distance squared. And we just think of this as what? Same thing goes if you try this in section 14.7. This just allows us to avoid the radical. If you didn't know that, when it comes to finding in terms of maximize or minimize in distance, optimization, you can maximize or minimize distance squared, you get the same answer. If you want us to prove it, we can. We can do some little implicit differentiation. You know, you just would divide that thing out in the end. It wouldn't factor into the problem at all. So when here's our function right here. There's our function of x, y, and z. There's our constraint. So our first step is, you go, what's step 1? You got to find del f and del g. And in front of del g, I want you to put the lambda symbol. All right, so what's del f? Which in this case, I don't care if you call it del. Do you want to call d squared now f? All right, so what's del f? Don't we make a vector? That's a vector. Gradient of a function is a vector. Well, it's made up of all the partial derivatives. Fx, fy, and fz. What's with respect to x? Partial with respect to x. All that mess. The beauty of this section, everyone, you don't have to substitute a z like we did last time. Remember that? But if you did want to work this problem by 14.7 technique, you would have to replace the z with something. Could you do it? See, that's what I mean. You could do this problem, like even on a test, you go, that's not sure I'm going to use the technique from 14.7 to solve this. By all means, you could. But you'll see a nice elegant method here too as well. This is just what? 2 times, and that's it. What's this derivative? Partial derivative. And this is just 2 times e plus 3. Everyone agree? These are the partial derivatives. Now come over here. What's del g? Oh, and put a lambda in front of it. Lambda del g. All right, what do we get here? That means I'll put del g down, then I'll just distribute a lambda everywhere. I can put this in. They share the common gradient vector. This is easy. What's their respect to x?
1, 1, 1.
This is what makes this technique easy. A lot of times you're constrained. You get those partial derivatives, you go, oh, these aren't bad at all. Now you have to distribute the lambda to all of them, so this is 1 what? 1 lambda, 1 lambda, 1 lambda, so I'm just distributing it. This is what we do. This is the system we gotta solve. Solve this system. Now if we get more than one answer, all we have to do with our, say we got 3 answers, we'll just check them all to see which one gives us the shortest amount in terms of distance. Go back to the distance rule. But if we only get 1 answer, I'm pretty sure that 1 answer is it. Do you agree? There you go. So that's the idea. You go, what if I got 4 answers? In the final step, just take all 4 answers and see who wins. Put them back into this. We gotta solve this system. Now this is what happens with Lagrange multipliers. Your system is set this equal to this. Corresponding components, set this equal to this. Set this equal to this, and then there's one more thing. We gotta list a constraint. Alright? So I'm gonna do this. Here's the system we gotta solve. What's 2 times x minus 2? What's that gotta equal?
1 lambda.
1 lambda. I'll put and. What's the next part? 2y must equal
1 lambda.
lambda. And 2 times c plus 3 must equal the.
3.
This is the biggest error. I've taught this for years, everyone. Even students would have like the technology to solve this. You know, like a TI Inspire where it has a solve system button. And it comes out not working out because they forget to list the last constraint. You always list in your system the constraint for your problem. What's the constraint? Always add that. You can do it at the beginning or at the end. What's my fourth thing? This is the system of equations you're solving right here. It may look long, but it's not that bad. We're a couple minutes away from getting this thing solved. All we gotta do is solve that system. So this equivalent to this one equals this equals this, and this. So we got 4 equations. How many variables? X, Y, Z, and lambda. But we'll still solve it. Alright, so we gotta get started with this. Let's see. What do y'all think, everyone? I could solve for X here in terms of lambda. I could solve for Y here in terms of lambda. Was it lambda over 2? I could solve for Z here in terms of lambda and substitute them all in here and everything would have lambdas. And once we get lambda, we can get all the numbers. Let's do it. So 2x minus 2 distributed equals lambda. What would x equal? 2x minus 4 equals lambda. What's x? Lambda plus 4 over 2. Did I do it right? Yeah, I'm not. Thank God, I'm going to need to back me up. Thank you. What's y equal to?
Lambda over 2.
Alright, what's z equal to? I gotta distribute this first. 2z plus 6 equals lambda. So z equals lambda minus 6 all over. You ready to jam it in here? Lambda plus 4 over 2 plus lambda over 2 plus lambda minus 6 over 2 equals 1. Boy, we solve that, get lambda, we're going to have this thing solved up. We'll plug it back into this. Got them right here. All ready. All we need is lambda. You want to multiply 2 on both sides? Multiply 2 on both sides, and then get your common like terms. So if I multiply 2 on both sides, those 2's are gone. But this turns into 2. What's lambda plus lambda plus lambda? 3 lambdas. What's 4 minus 6?
-2.
And I now have 3 lambda minus 2 equals 2. So 3 lambda equals 4 with lambda.
4/3.
And now I'm smiling because all we gotta do is put that in there, here, and here. We got x, y, and z, get the point. Just say find the point on the plane, we'll get it. Let's see what it is. What's x? Well, you don't mind fractions here. What's 4/3 plus 4 over 2? And y, what's 4/3 over 2? Feel free to use technology if you don't like fractions so much. What's 4/3 minus 6 over 2? Those 3 numbers are going to be the point. 4/3 plus 12/3. 16/3 over 2. 16 over 6, what's that reduce to?
8/3.
Is that 8/3?
Mhm.
Someone hear that? What's y equal to? Y equals 4/3 divide 2. 2/3?
Mhm.
Let's see. What's 4/3 minus 18/3? What's negative 14/3 over 2?
Negative 7/3.
Negative 7/3. Yeah, I always worried I make a little arithmetic error where you term, pre-algebra in terms of like adding and subtracting fractions. So I want to check this. Does that make this statement true? That one right there? Did these all add up to 1? Because it's got to be under that constraint. I mean, it definitely has to be all add up to 1 here. 8/3 plus 2/3 is 10/3. 10/3 minus 7/3 is 3/3. Yeah, we're good. Now that's the point on the plane. There's the answer. This is the point on that plane, x plus y plus equals, that has the shortest distance in three-dimensional space to that point. Shortest distance. Isn't that cool? Hey, actually, the problem out of the book, if you're curious, they wanted you to find the distance. I reworded it like this, but what would you have to do if you had to find the distance? What would be the last step? Just plug it in here. I just think it saves time, especially on a test. Just to say, get the point. Because I knew you could plug it into the distance. So, and keep in mind, you could have used 14.7 technique. I do like a problem like this, seriously on a test. Many times I like to give you that option. You can do it by this method or by that method. If you did 14.7 technique, the only thing you had to do was what here? You wouldn't have had this, in terms of F, you wouldn't have like gradient vectors. You would just replace the Z in terms of solving right there, what is Z equal to? 1 minus x minus y? That's what we've done that section. You would have taken this and what? You had a function of x and y. Cool. Alright, hey, last problem. Let's look at another one of these. So, that was number, you want to know which problem that was number 39. But it wasn't in 4.8, it was in 4.7 because in 4.8 they have you go back to 14.7 and work the same problems. Because they're trying to show you that you can use either technique to solve it. So this is number 47 from section 14.7. Find the volume. Okay. Find the volume of the largest rectangular box. All right. Optimization. Largest rectangular box. In the first octet. With 3 faces in the coordinate planes. All right, with 3 faces in the coordinate planes. And 1 vertex in the plane x plus 2y plus 3z equals 6. All right. I always like to look at this problem. I'll start drawing some pictures and stuff. I like to look at it. Figure out what's that F and what's the constraint. So what are we trying to optimize? Maximize and minimize. Volume, very good. That's what we're doing, the volume. We're trying to optimize volume, we're trying to get the largest volume, maximum volume. So where's the constraint? There it is. It's almost like you can go, oh, this is the other equation? Yeah. This is one equation, there's my constraint. That's my G, right there. Because 1 vertex has to be in that plane, right? Constrained to that plane. It wasn't like, oh, that vertex can be anywhere in quadrant 1. Exactly. So, if you want, we can even draw a picture. Because they said this thing's in quadrant 1, or octant 1. picture always helps, we're just gonna draw a box. Do you remember how to graph that plane? Like what would be the x of
1.
6?
Or 6, yeah.
Alright, 6. I'm gonna put 6. What's the y-intercept? 3. And 2. So there's that plane, but I don't understand, only one point of the box can be in that plane. So this box may look something like this. It may not be big. But it might be a box like this. I'll draw it like this. And you're talking, your box might be just that big. Like one face on this side, one face on this side, but one of the corners is hitting that what? That ramp coming down, that plane. That's what's happening here. So it's the idea of like, okay, I'm going to have one face over here, one face over here, but it's going to come up, and that corner of that box is going to hit this portion of that plane, that triangle there. Well, that picture doesn't have to be perfect. The key is, I can draw this box bigger. What two variables you want to use? You want to use x, y, and z? I like that too. X, y, z. Sound good? So I'm going to start out. V of x, y, and z is x, y, z. That's the function you're trying to optimize. What's the constraint? Our constraint is
X plus 2y plus 3.
x plus 2y plus 3z equals 0.